First of all, I'd like to thank the organizers for inviting me and giving me the chance to speak here. So everything I'm going to talk about today is joint work with Svante Jansson from Uppsala University. And it's a topic really that lies at the intersection, say, of probability and combinatorics, where I think some input maybe of some physical ideas might be useful. So what is the motivation here for this project? So the motivation was really to study the number of copies of H in a random graph G and P. Okay, so think of maybe for the moment of you want to count the number of triangles, you want to count the number of force cycles, and so on and so forth. This is a very important quantity in random graph theory. I would actually say it was a driving force in the development of random graph theory. So for example, if you look back into the very early papers on random graphs, just the question, does the random graph G and P contain a copy of H? This was addressed in one of the very first papers on random graphs by Adarsh and Rainey using the first and second moment method. In fact, they only obtained some partial results for these graphs. This was later refined by Bolobash in the 80s. It was fully resolved, getting a better understanding of the second moment method, I would say. Furthermore, the number of copies of H has been a test bed for a number of other methods. So for example, the method of moments to establish Poisson convergence, or also the Stein-Shen method was also applied to this random variable in some early work by Babur. Furthermore, also some more classical questions, maybe from probability theory, like asking the question, when is this random variable asymptotically normal, was also studied for this random variable in the late 80s by Andrei Rudzinski. And each time one can say that the application or the study of this random variable has usually led to a deeper insight into some of the tools and techniques that we're nowadays using. For the purpose of this talk today, I want to focus here on maybe the following result here is really the most classical result in this direction. So we're asking when or what is the probability that your random graph G and P contains no copy of H. So there are a number of different motivations for studying this random variable. Some maybe come more from some extreme Low-Ramsey type question, but I think in general this is also on its own a very interesting question, say just in probability theory. And it was a very, I would say, breakthrough result in the late 80s by Jansson, Vucak, and Rudzinski, who showed or who were able to nail down the probability that your random graph contains no copy of H, say up to constant factors in the exponent. Okay, so they were able to show that the probability that your random graph contains no copy of H decays exponentially in this parameter phi of H, where phi of H comes from a certain minimization problem. And if you've not seen this before, so the reason why this quantity is perhaps not so simple as you would like is that in some sense you need to search for the reason why your random graph G and P contains no copy of H. So for example, if I draw some clique with some one sort of outgoing edge attached to it, then it turns out that actually the real reason why your random graph will not contain such an object is basically because it will not contain a copy of K4. So in some sense, you must look for the main obstacle. And this is sort of where this quantity comes from. So maybe from the modern perspective, what does the probability of having no copies at all mean? Well, we can interpret this as a special case of the lower tail problem, where the lower tail problem asks for what is the probability that your random graph has too few copies of H. And one way to quantify is that we want to say your random graph contains 1 minus epsilon times the expected number of copies. And then you can ask, can we get a similar statement? And when I started looking at this some years ago, I was quite surprised that actually this question had not been answered in full detail. So there were only some upper bounds available on this probability, but there were no matching lower bounds, which actually proved that these results were essentially best possible. And this is something we did here with Svante Jansson. We were able to basically extend this result to the case where we look at the lower tail. We're looking at the probability of having 1 minus epsilon times the expected number of copies. And I should mention at this point here that maybe the form of this result is perhaps not quite of the standard form, because, for example, if you take maybe the perspective of large deviation theory, then often, for example, the n0, how large the graph needs to be, might depend or is allowed to depend on your parameter epsilon. This result here is uniform in the sense that it holds for n larger than some absolute constant. There's no dependence on epsilon here. The only key restriction is that we want that this epsilon squared times this parameter phi h is big. And in some sense, that's a very natural requirement because you want to study exponentially small probabilities. And the probability in question decays exponentially in epsilon squared times phi of h. So it's a very natural assumption or a condition that we want that this parameter is not too small, say at least some constant. Okay, so why should we care about this? What is the motivation? So I've already mentioned that in some sense, at least in random graph theory, the study of this random variable has been quite influential. So the number of copies of H has really become a standard test bed in the area of concentration inequalities. So if you develop new tools and techniques, then typically you'll try to showcase your methods using these copies of H. We've seen one example of this, for example, on Monday in the theory of nonlinear large deviations. Yes?
Just coming back to your previous point, so do you know that you need this condition, that epsilon squared times phi of H, or is it possible that the result holds without this condition?
Well, okay. So I'm sure, I think one can sort of patch things together, because what this is just saying is that if this condition is violated, then the probability in question will be something like 0.999 or something like that. And then you can use other methods to determine such constant probabilities, say use normal approximation. So, just maybe to elaborate on this, it turns out, maybe as a fact, use maybe a different color, that this is somewhat of the normal approximation form. So you can, if you look at, say, epsilon squared phi of h, this is sort of up to constant factors and ignoring sort of degenerate cases when p tends to 1 or something like that. This is essentially this here. Okay, so this is sort of really of this Gaussian type form. So if you apply normal approximation, then the other range, you'll get exactly the probabilities you're interested in. Yes?
Your phi of h will go to infinity, right? So you're interested in epsilon going to 0 or general epsilon?
Okay, so the point of this formulation is that I don't need to make an assumption, basically. So, okay, let me rephrase this.
Epsilon cannot exceed 1.
Yes, but epsilon can go to 0 at a certain rate. So this allows for epsilon going to 0. So you might be interested in the case where your epsilon is very, very small.
Epsilon is constant.
So epsilon is not.
It doesn't matter. Actually, it's true for all epsilon, but
yes, as long as
it's not meaningful when epsilon is constant. Not so much.
Well, if it's a constant, yes, then I know this is just some number. I mean, so we really want to understand what is the qualitative behavior on epsilon in this case. Okay, so maybe your question is related to maybe in large deviation theory where you really want to nail down the constant. I think this.
In large deviation, usually the difference in epsilon going to 0 at the same time that phi of h goes to infinity is considered kind of slightly moderate deviation because it did not deviate much from e of xh, and then your understanding of the fact that there is epsilon squared is already telling you something. But if epsilon is 1/2, then the fact that there is an epsilon squared tells you nothing.
Yes, that's right.
You don't have the constants.
Only in some cases, but we can come back to that later. I should maybe mention that my main motivation is a little bit more from the applications perspective. So I'm more than happy here to give away a factor of 10,000 if that means that I can apply the result for a wider range. So maybe I cannot only apply it for dense P or for the dense case, but I want to cover the entire range, then I'm very happy to give away some constant factors there. This is sort of the perspective from the random graph perspective, I think. Okay, so this was the question concerning motivation. One was sort of this development of tools, and the second question is exactly what we already discussed. It sort of falls into a section of concentration of measure and large deviation theory, and in some sense this here is sort of more like a concentration inequality type. You get uniform bounds. Okay, so after this motivating example, what is sort of the the general outline that I'm trying to aim for. So first I want to introduce a tool that's very widely used in random graph theory. Perhaps it's not so well known in other communities, which is a concentration inequality for the lower tail. And our main aim will be to basically match that in what I would call the so-called Poisson case. Okay? So this thing will give an upper bound, and we want to give sort of up to 1 plus the law of 1. We want to match that from below, showing that the thing is essentially best possible. However, the drawback of this very precise result will be that it only applies in the Poisson case. So to cover the non-Poisson case, we need to do some extra tricks. And if time permits, I also discuss what open problem, namely concerning the question what's the probability that the random graph contains no triangles. Okay, so let me maybe go to this so-called Janssen's inequality. So the way I want to present it here is in a slightly simplified setting, but I think it captures the spirit. So we want to look at some binomial random subsets. So we're given some set, say, gamma, and we include each element independently with probability p. Okay, and if you want, you can also say that element I is included independently with probability pi. So this is just a product space. And then we have some collection of edge subsets S. And we're interested in how many of these edge subsets are present in this binomial random subset gamma p. Okay, so think of, for example, we want to copy how many triangles does the random graph have. Then what we're interested in, how many 3-element subsets forming a triangle are present in the edges of your binomial random graph. One way to formalize this here is to say, let's look at X as a sum of these indicator random variables, where the indicator represents the event that your set A is contained this binomial random subset. Okay, so think again of the triangle example. S will be the collection of 3-element subsets forming a triangle, and then this event is just evaluating to 1 if all these 3 edges are really present. And you might wonder now how sort of general is this? What are the real restrictions? And the real restrictions will be that somehow we're looking at the sum of indicators, but they need to have a special form. They need to be basically increasing. That's the key limitation here. So to state the inequality, let me maybe very briefly introduce one more parameter, though perhaps it's not so crucial. So first of all, just to unify the notation, I always denote by mu the expected value of x, which is of course nothing else than the sum of these indicators. And then I want to introduce one more parameter, delta, which will somehow measure how dependent are my random variables. And one way to do that is to say, okay, I want to sum over all pairs of overlapping indicators, meaning of all pairs of indicators which are dependent. So, for all pairs AB in S, where A is not equal to B, and where they have some intersection. Okay, this just means that that these two indicators AI and AB, IB, that they'll be dependent. And somehow this will measure how dependent are these random variables. And the key point is, if for example you look at independent summands, then this parameter will be 0. So in general, the idea will be if this parameter is very small, then there's not too many dependencies. If you think again of the triangle example, what this basically is measuring, it's measuring the expected number of pairs of overlapping triangles, and you're renormalizing it by the expected value. So if this parameter is very small, this means that at least in expectation, most of the triangles should be disjoint, which is sort of very natural for the Poisson range. Okay, so now that we've discussed the setup, let me maybe just state this Janssen's inequality, which I think is very nice. I should say the name Janssen's inequality, I think, was coined by Joel Spencer, not by Janssen itself. And so what this inequality basically says is that you get some Chernoff-Bernstein type inequality in the case where you have dependencies. Okay, so you're looking at what's the probability that x is at most 1 minus epsilon times the expected value. And you get some upper bound of the form exponential in some parameter phi minus epsilon times the expected value divided by 1 plus delta. Okay, and take my word for it, if delta is equal to 0, this is exactly the same expression you would get if you apply your standard moment generating function technique, this Chernoff type technique. Okay, so the main punchline here is if delta is 0, you actually recover the classical Chernoff type bound. And I should say that when this inequality was first developed in the late 80s, it was really quite a breakthrough. It really changed a lot of the way proofs were working, because this gave access really to these exponentially small probabilities, which at the time were very, very difficult to get. And still nowadays, this is really widely used in probabilistic combinatorics or combinatorial probability. So it's very natural to ask, we have this very widely used tool, how good is it? What can we say about the quality? Are we giving away a lot when we apply this in proofs? And now, so if you're asking yourself, how good is my concentration inequality? There are different ways we can play the game. One way to play the game is to say, I just show you one example where it's best possible and argue, okay, so we cannot improve it. If you want to play that game, okay, it's very simple. Just look at the independent case where delta is equal to 0. This just reduces to Chernoff bounds, and we know that Chernoff's bounds are best possible. Okay, but the question is, what does this really tell you? Right? We introduced this inequality exactly to cover the dependent case. So if you argue that in the independent case it's best possible, that really doesn't tell us very much. Furthermore, I'm really aiming more at the inequality of the form, if your random variable satisfies a few conditions, then it's best possible, no matter what your random variable is, as long as it satisfies these conditions. Okay, so in particular, maybe one thing that might seem intuitive is that if you stare at this form for a while, well, as long as delta is pretty small, we're sort of close to this Chernoff type exponent. And furthermore, the delta parameter said, well, the delta measures the dependency. So as long as delta is small, this exponent here looks Chernoff-like. So maybe there's some hope that it's still best possible in that case as well. So maybe we can prove a lower bound of this form if delta is equal to delta's little o of 1. Maybe we can sort of prove a lower bound of the same form up to this little o of 1 term here. Okay, this is sort of more than the large deviation context. And so this is what we're able to do in the approximately Poisson range. Okay. So let me maybe introduce one more parameter for this. So this parameter will sort of say it's the maximum over the expectation of these indicators. In other words, it's an upper bound for the probability that one of your indicators is 1. And so what we're able to show is that if delta and pi, this parameter we just introduced, go to 0, and epsilon squared times the expected value tends to infinity, then we can sort of nail down the asymptotic behavior of this probability exactly as this function. This phi of minus epsilon times the expected value. Okay, so this gives us a very good control over this lower tail probability. And you might now ask yourselves, what about these conditions? Are they natural or not? And so I think that here this assumption that epsilon squared mu tends to infinity, that's a very, very natural assumption, because here what we're saying is we're looking at a decay that's exponential in epsilon squared times the expected value. So if you really want to study exponentially small probabilities, this quantity better should go to infinity. But now the question is, of course, what about these other two parameters? So let me perhaps mention that, for example, if you apply, say, the Stein-Shen method here, then one thing you can show is that the total variation distance between x and a random variable, that is a Poisson random variable with expectation mu, is bounded from above exactly by the sum of these two parameters. So this is Stein-Shen. So in other words, if delta plus this pi both tend to 0, then really you can say that your random variable is approximately Poisson. So in that sense, this condition is quite natural. In fact, I would say that if we even go on a high level, both of these conditions are conceptually very natural, because how do we usually teach the Poisson paradigm? We say that if X counts many rare, almost independent events, then your random variable should be approximately Poisson. Okay? And so when are these events rare? Well, that's when each of these indicators, when that tends to 0, so that satisfies this property. When are they mostly independent? Well, that's the case when exactly this dependency parameter delta tends to 0. And that we're looking at many events is, for example, also implied here by this assumption. Okay, so under these two very natural assumptions, we can nail down this probability. And then we already discussed it a little bit here. Here, there's no hidden parameter that we assume to be large compared to epsilon. We just make these assumptions, and under these assumptions, we can prove this asymptotics. Okay, so it's a very, I think, satisfactory answer to this question. Furthermore, if we say relax the condition that delta is tiny, well, we can still say something, maybe not as precise as this here, but we can still sort of tell you the decay up to constant factors. Okay, so let me say one or two remarks here. So again, the main contribution of this work was to prove a matching lower bound. The upper bound, this was already following from this Janssen's inequality. And if you've not seen this before, so for the special case epsilon equal to 1, it's very easy to construct a matching lower bound. But unfortunately, that does not extend to the general case. But let me still briefly indicate that, how the special case epsilon equal to 1 goes. So it's like it's from a modern perspective more like an exercise, or maybe not even an exercise. So it's just the observation that we're in this setting where all the random variables are increasing, so we can apply FKG. So this is this Jansson, Wutschak, and Rudzinski lower bound. So they just said, okay, let's look at the probability that x is 0. Right? Because we're looking at the sum, this means that actually we can write this as the following: intersection of the events that all the individual elements are 0. Now, each of these events that your indicator is 0, right? This is sort of, recall, each of these things is an event of the form, are these and these edges present, for example, in my random graph? So all these guys here are decreasing events. So in the product space, so we can apply FKG. Or actually here, Harris inequality would be enough. So this is lower bounded by this product. So now we just do the usual rewriting, write this as 1 minus, this expectation. In order to convert this product into a sum, then we need to use the fact that delta tends to 0. Okay, because this means that each of these elements here will be small, then we can and we can convert this into a sum, so this will just then become so this is sort of in the special case epsilon to 1. It's very simple, but it's not at all clear how to extend such a calculation to the general setting, at least under these minimal assumptions. Okay, and I'm not going to say too much about it, how this proof actually works. So let me just mention that it uses a variety of different things. So we start off with some kind of Hölder's inequality, then use correlation inequalities to estimate the logarithmic derivative. And perhaps for the experts in the room, one thing I find quite nice is that we're able to estimate, in some case, the fractions of certain of these Laplace transforms by integrating the logarithmic derivative not from 0 to something, but from, say, s half to s. But really, if you're interested in the technical details, I'll refer you to the paper for the moment, or ask me afterwards. So what about now the delta tending to infinity case? Right, so far, far I said, okay, we can nail down this exponent very precisely if delta tends to 0. We can get it up to constant factors if delta is at most order 1. So what about the other case? So it turns out that under certain symmetry assumptions, you can, in some sense, always reduce to the Poisson case, at least if you're interested in a lower bound. So in some sense, the strategy will be the following. Suppose you're interested in the probability that you have too few copies of XA, of your graph H. Then, so maybe here this delta parameter tends to infinity. But what I can promise you, and I'll show that a little bit on the next slide, is that there's some other graph, which is a subgraph of J, which is in this Poisson range, where the delta parameter is order 1, which is related in this very nice way to the original probability. Okay, so the probability that XH is too small is at least a constant times this other probability. Okay, and the nice thing is now, to this probability, now we can apply our lower bound again and sort of bootstrap the probability in question. So let's have a quick look at this. So for the purpose of this talk, I decided to use one graph, which I think is called this House of Santa Claus. So it's a very popular thing, at least in Germany, for children. So what I mean is this graph here, when H is this graph here. Okay, and so if you apply the machinery that we've seen so far, then you would get the following two estimates. So it turns out that if p is very small, say at most n to the minus 1/2, then we can nail down the probability very precisely. And if we're in this intermediate range, we can still get it up to constant factors. Okay, but what about the remaining range of p? Well, what is the reason why our methods, or the methods that we discussed so far, why do they break? Well, let's just look at this copy of K4 in here. If p is much bigger than n to the minus 1/2, then the expected number of neighbors, say, of just these two vertices is very big. Okay? Because what's the expected number of neighbors? That's np squared. And np squared tends to infinity if p is much bigger than n to the minus 1/2. So in other words, what this is saying is that if p is much bigger than n to the minus 1/2, you simply will have overlapping copies of this Santa Claus graph just because the codegree will be extremely large. Okay? So in that range, you cannot anymore hope for any kind of Poisson approximation. Okay, so this is sort of bad news. This technique does not work. But maybe you can still try something else. So if you do the calculation, say for p between n to the minus 1/2 and n to the minus 2/5, you'll notice that what this Janssen's inequality tells you is that, say, the exponential decay scales exponentially in epsilon squared times the expected number of copies of K4. Okay? And now the observation, and when I first saw this, this was really, now you think it's something magic is happening. So the idea is, or it turns out that if p is in this range, then this delta parameter for this K4, this will now be order 1. In fact, if p is much smaller than n to the minus 2/5, it's actually little o of 1. So now, at least for K4, we can apply our usual lower bound and get something of this form. So now just the question is, how can we relate maybe the number of K4s to the number of copies of this Santa Claus graph? So what we're going to do seems very very generous on first sight. So what are we interested in? We're interested in the event that we have too few copies of this graph. So to make my life easier, I'm going to introduce here this event dj, which says that the number of copies of j is too small. So what we're really interested in is this probability of this event. And now I'm just going to be very generous. I'm going to do something that might seem strange on first sight. So I'm going to say, okay, this is bounded from below by this event. that we have too few copies of this graph and too few copies of H. Okay, so note, I've now sort of thrown in an extra event that's exponentially small. Seems like we're giving away a lot. But once we have this form, now we can rewrite it as the probability that we have too few copies of K4 multiplied by the probability we have too few copies of H conditioned on having too few copies of K4. And the nice thing is we know how to apply lower bound to this. So if we get some control of this conditional probability, we're in pretty good shape. Let's maybe do a quick check in some border cases. So let's look at epsilon equal to 1. In case epsilon equal to 1, we say trivially have what? So let's just rewrite this now, make this explicit. So we're interested in the probability of having too few copies of this Santa Claus graph, conditional on having too few copies of K4. Okay, but in the special case epsilon equal to 1, we can just rewrite this. We can just say, okay, this is equal to the probability that we have no copies of H, conditional on having no copies of K4. And in this case, it's trivial. If you have no copies of K4, you can have no copies of H. Okay, but again, if you want to do anything like that, when you have some epsilon number of copies involved, then things get more messy. Okay, but so this is sort of the plan that they outlined here. Is we write this in a sense saying, okay, we want a lower bound on this event. We basically blame all the error probability for this other event, and we just need to make sure that this conditional event is in good shape. So somehow there might be, or there seems to be, at least from the philosophical point of view, some relation to tilting, although I don't quite understand whether there's a formal relation or not. Because if this is true, if this is now holds with probability, with constant probability, then what we really did is we took an exponentially small event, that we have too few copies of K4. We conditioned, the event that we have too few copies of H, and we conditioned on another event, and this boosted the probability from being exponentially small to constant probability. Okay, so we really converted a very atypical event into a typical event, which, at least from the philosophical point of view, is related to this tilting idea in large deviation theory. Okay, and I think if we sort of stare at this picture here again for a while, right? So if we're saying too few copies of K4, how many copies of H? It sort of seems obvious. It at least seems obvious. If you have too few copies of K4, we should have too few copies of H. But of course, the question is, how can you prove something like that? So let me maybe try to draw one more picture here. So let's maybe look at the distribution of XH. So XH, we know that it's asymptotically normal, so it'll have some nice shape, maybe something like this. And say here's the expected value. And in sort of the unconditional world, this event is maybe over here that we have at most 1 minus epsilon times the expected number of copies. So this is exponentially unlikely. But it turns out, and this one can actually prove, if you condition on having too few copies of K4, then you suddenly are able to massively decrease the expected value. So the expected value drops from the expected number of copies of H to 1 minus epsilon times the expected number of copies of H. So this one can prove. So in other words, the say the distribution of XH conditioned on this other event intuitively should look different. So I don't have a proof for the fact that it really looks like this, but intuitively you would expect something maybe like this, where now the new expected value, so we're living in this conditional space, where now this suddenly becomes at most 1 minus epsilon. Okay, so really on an intuitive level now, it really should look more like this. Sort of what should be going on. And if you think about this, how this Santa Claus graph is built, you can basically think of how do we count all copies of H? Well, we first count all copies of K4 and then sort of try to extend each copy to the Santa Claus graph. And then maybe using symmetry we can do something. But it does not seem to be so easy to make such a statement fully rigorous. However, we were at least able to prove some variant of this which was sufficient for our purposes. Okay, so for those of you, maybe one of the main difficulties is that while it might be easy to calculate here, so the first moment in this conditional space, calculating the second moment, or in general the variance in such a conditional space, seems quite tedious, and without some extra tricks we did not know how to do that actually.
I have a question for that precisely. You could write this, so say if you're interested in Santa Claus, you could write it as a sum of, so if you have the K4, all you need is these other two, you know, the roof. So this is like so you have the indicator for the K4 plus an indicator for the roof. And these are independent, right?
Yes, that's right. So this is the way you can prove something like this. So what you do, let's see, let me write it over there. So this is true, say in general, that you can write, if you're interested in, say, the number of copies of H, you can, and this is true for any subgraph actually, you can always factor it in some renormalizing condensate CGH times the expected number of copies of G multiplied by some other expectation. So let me denote it by Y G of H, where this sort of says, if I give you a copy of G, how many extensions are there to a copy of H? Okay, so in this case, G would be the copy of K4, and then we would need to extend the thing. So this is by symmetry, you can always prove that. And basically, using correlation inequalities, you can prove something similar in the conditional space. So it turns out that if you do the calculations, and I don't want to do them here, you can actually prove so this example, G is equal to K4, so let me maybe rewrite this. So you get basically the same expression, and then just by definition of this event, this is so this is just by definition of this event. So this shows that this is at most 1 minus epsilon times the expected number of copies of H. Okay, but this requires some argument. This uses some correlation type arguments. But it's not so clear how to do this for the second moment.
So I guess my question was more in the direction, you can write XH as a copy of two independent indicators, right?
Yes.
So the idea was, instead of looking at the variance, you could compute the cumulants, right? So that's my question. Because the variance, of course, is very ugly to compute. Mm-hmm. although there is a conditional formula for the variance, but for the cumulants, you could in principle compute any, so kth order cumulant because they're linear. You have a sum of independent things.
Let's maybe discuss that after the talk. That would be quite interesting. Okay, so so this was this reduction step where we said somehow we can reduce from having too few copies of H. We can blame it to having too few copies of K4, and this is the way we can get our lower bound. Okay, assuming that we can implement this step, but that requires some more care and technical calculations. So just take my word for it, you can implement this strategy for any graph H. On an intuitive level, what you can do if you, for example, want to prove such a statement is that for proving the lower bound, you should always focus on the graph which attains the minimum in here. Then you can apply this reduction to that graph, and it turns out that it works, but it requires some arguments. And the nice thing about this formula somehow is that it tells you that really, at least up to constant factors, you're pretty much consistent with any kind of normal approximation arguments. You have this nice form here in the exponent. Okay, so let me maybe skip this one and maybe just come to sort of an informal summary what we looked at. So we were interested in lower tail probabilities, and one of the motivations was to really show that this tool that's quite widely used in probabilistic combinatorics, that's often close to best possible. So we saw that, for example, if we have certain natural Poisson conditions, we can nail down this deviation function asymptotically, at least on a logarithmic scale. And this allowed us here to resolve the subgraph question I mentioned at the beginning. And I think this, at least conceptually, this reduction to the Poisson case is quite a cute idea. And I just want to finish with one open problem where I think I hope there's some kind of soft argument that might be able to give something like that. Namely that I'm interested in, can we prove that the probability of having no triangles in a random graph, when p is a constant times n to the minus 1/2, that this scales as some function of c multiplied by n to the 3/2. Okay, so I know that the order of magnitude n to the 3/2 is correct, but I don't know that there exists such a function that this is true. And you might ask, why am I interested in exactly in that range? Well, the point is, I can answer this question for any other p. This is the only range of p where I don't know how to do it. And sort of as a final remark, so I always dream that someone would just tell me that this is sort of an easy application maybe of some kind of interpolation or subadditivity argument, but I don't know how to do that. Let me just briefly indicate sort of one naive to prove this.
Lower bound, upper bound, equality.
I mean, there are some upper and lower bounds, but I don't know if any of them is best possible. So I would say prove that such a function exists. I would even be happy if you just prove that this exists. Even if you don't tell me what the value is, I would already be very happy.
Because matching lower bounds up to theta you have, that's...
Yes, so the order of magnitude is n to the 3/2, but I'm asking, can you determine the precise dependence on c? Because for any other range, I know exactly what's going on. And so perhaps, I mean, this is more meant as sort of a, not maybe too serious attempt, but if you look at the probability that your random graph GNP contains no copies of a triangle, right? This in particular means that each of these subsets is triangle free, the first half and second half, so you can prove something like let's say N2P, which might scream for some application of interpolation method, but I don't know how to make anything work. And I'll stop here. Thank you very much.